The Antikythera mechanism has now been reconstructed after more than 2,000 years with the help of modern computational methods. When it was recovered from an ancient shipwreck beneath the Mediterranean, it looked like little more than a corroded lump of bronze about the size of a shoebox. But as researchers examined it with X-ray imaging CT scans and gradually uncovered Greek inscriptions buried beneath layers of corrosion, they realized they were looking at something extraordinary. It was what is now often described as the world's first mechanical computer. There was one major problem. Nearly half of the machine was missing. Its most mysterious section had been almost completely destroyed. No original blueprint survived. No complete description had ever been found. And for more than a century, no one could prove exactly how this missing part had once worked. Then came 21. A research team at University College London decided not to simply guess what the missing section looked like. Instead, they worked backward from the surviving inscriptions, ancient astronomical cycles, and the gears that remained. Using mathematical modeling and computational analysis, they attempted to reconstruct the lost mechanism from the evidence itself. The result was a complete system of gears that could account for nearly all of the surviving evidence from Antikythera. In this video, we will follow that reconstruction and explore what this ancient machine was truly capable of, how its missing sections may once have appeared, and what they reveal about a level of ancient Greek technology that still seems astonishing today. Content. In the spring of 1900, a group of sponge divers from the Greek island of Symi were sailing toward the waters of North Africa when a storm forced them off course. They took shelter near Antikythera, a small rocky island between the southern tip of Greece and Crete, and waited for the sea to calm. While they were there, a diver named Elias Stadiatis put on a heavy copper diving suit and descended beneath the surface. When he returned, he reported something disturbing. He said the seafloor was covered with decomposing human bodies. They were not bodies, they were bronze statues. At a depth of roughly 130 to 165 feet, the divers had discovered the wreck of a Roman trading vessel that had sunk around the 1st century BC. Inside was an extraordinary cargo of luxury goods. There were life-size bronze and marble statues, amphorae, glassware, jewelry, and coins from Pergamon and Ephesus. The Greek government sent naval vessels to assist with the recovery, and for months the divers brought objects to the surface one shipment at a time. Among all those treasures was a heavily corroded lump of metal, about the size of a thick dictionary. It had no obvious shape and appeared to be little more than a ruined mass of bronze. Almost no one paid attention to it. The object was taken to the National Archaeological Museum in Athens, along with the rest of the recovered cargo. There it remained in storage for nearly 2 years. Then in 1902, archaeologist Valerio Stais was examining the artifacts when he noticed something no one had expected. Part of the corroded bronze had broken away, revealing something inside, a gear. Its teeth were only about 1.5 millimeters long. They were evenly spaced, carefully cut, and astonishingly precise, comparable in refinement to gears found inside mechanical clocks many centuries later. That created an immediate problem. According to the archaeological record known at the time, the ancient world was not supposed to possess anything like this. Greece, Rome, Egypt, Persia, and China had all produced sophisticated technologies. They had wheels mills, pulleys, water systems, and complex instruments. But nothing previously discovered from this period contained a comparable network of finely cut gears designed to transmit precise rotational ratios between multiple shafts. The bronze object from Antikythera seemed to stand completely alone. There was no obvious predecessor, no close relative, and no clear chain of technological development, explaining how such a machine had appeared. Yet an even greater problem remained. No one knew what to do with it. The bronze was too badly corroded to understand from the surface, and too fragile to dismantle safely. Thick layers of mineral deposits covered the fragments so completely that the boundary between metal and hardened marine material was often difficult to distinguish. During the early decades of investigation, some researchers suggested that it might have been a sundial. Others thought it could have been a navigational instrument. A few proposed that it was simply part of a statue. Almost no one seriously considered the possibility that hidden inside the corrosion was a true mechanical machine. The idea seemed too advanced for the ancient world they thought they understood. And so, the object remained in the museum for another half-century, until a British physicist decided to find a way to see inside it. Derek de Sola Price was not an archaeologist. He was trained as a physicist and later became a historian of science, eventually teaching at Yale University. In 1951, he began studying the Antikythera fragments and quickly realized that the object in front of him was unlike almost anything else known from antiquity. For the next 2 decades, Price studied photographs, measured proportions, and compared the fragments with surviving ancient texts. During his research, he encountered a passage written by Cicero, the Roman statesman and lawyer who lived during the 1st century BC. Cicero described a device associated with the mathematician Archimedes of Syracuse. It was a bronze sphere capable of reproducing the movements of the sun, the moon, and the 5 wandering stars, the 5 planets visible to the naked eye in the ancient world. The description bore an unsettling resemblance to the mysterious bronze fragments stored in Athens. In the early 1970s, Price began working with radiologist Charalambos Karakalos in Athens. Between 1971 and 1973, they used gamma imaging and X-rays to examine the fragments from within. What they discovered transformed the investigation. Hidden inside the corroded bronze were at least 30 separate bronze gears. 27 could be identified within the largest surviving fragment, while 3 additional fragments, each contained another gear. These were not randomly arranged pieces of metal. They meshed together in a clearly deliberate mechanical system. In 1974, Price published his landmark study, Gears from the Greeks. His conclusion was explicit. The Antikythera object was not decorated. It was not a ritual artifact. It was not a simple clock. It was a mechanical astronomical calendar computer probably constructed sometime between 150 and 100 BC. Price emphasized just how extraordinary this was. Countless wheels from ancient carts had survived, but nothing else. From the ancient world resembled the delicate gears and compact mechanical systems preserved inside the Antikythera fragments. Yet Price had reached a barrier he could not overcome. The X-ray images were flat and two-dimensional. He could see the shadows of gears buried inside the fragments, but he could not determine exactly how they connected. He could not tell which gear sat above another, which shaft passed through which assembly, or how the individual layers interacted. The mechanism remained a mechanical labyrinth hidden inside bronze, almost like trying to read an engineering blueprint through frosted glass. Price died in 1983 without ever seeing the complete picture, but the technology required to look through the bronze 1 layer at a time, 1 millimeter at a time, at a level of detail impossible for the human eye was about to arrive. In 2005, the Antikythera Mechanism research project, known as AMRP, carried out microfocus CT scans of all 82 surviving fragments. Microfocus CT is very different from an ordinary X-ray. It captures thousands of extremely thin slices through an object from multiple angles, then reconstructs them into a 3-dimensional model at a resolution of less than a millimeter. For the first time in more than 2,000 years, researchers could separate individual gear shafts and overlapping mechanical layers buried inside the fragments without physically touching them. But the greatest discovery was not hidden in the gears. It was hidden in the writing. The CT scans revealed more than 3,500 ancient Greek characters engraved across the internal surfaces of the mechanism. These inscriptions had remained buried beneath corrosion for 2 millennia, invisible to the naked eye, and largely inaccessible even through conventional X-ray imaging. They were in effect an instruction manual, engraved directly onto the machine itself. They described its dials, its functions, and how the information displayed by the mechanism was meant to be interpreted. And what they revealed transformed the understanding that Price had begun decades earlier. The rear face of the mechanism could now be reconstructed in remarkable detail. The upper spiral dial, arranged across 5 turns, tracked the metonic cycle. This cycle contains 235 lunar months within exactly 19 solar years. After that interval, the phases of the moon returned to approximately the same dates in the solar calendar. A smaller subsidiary dial above it recorded the names of major Greek athletic festivals, including Olympia Pythia, Isthmia, Nemea, Na, and Haliaea. The machine could even indicate when major Greek games were scheduled to take place. The lower spiral dial, arranged across 4 turns, tracked the Saros cycle. This cycle lasts 23 lunar months, or roughly 18 years and 11 days. After that period, solar and lunar eclipses tend to repeat in a similar pattern. Individual cells on the Saros dial contain special glyphs, describing the type of eclipse, its approximate time, and other observational details. A smaller dial beneath it tracked the Exeligmos cycle, which equals 3 Saros cycles, or approximately 54 years. This allowed the mechanism to compensate for timing differences that accumulated from one Saros cycle to the next. The Antikythera mechanism was not simply counting days. It could predict solar and lunar eclipses decades into the future, using an astronomical cycle that Babylonian observers had recognized centuries earlier. But the most controversial evidence appeared in the inscriptions associated with the front cover of the machine. These lines described a complete planetary display. They referred to the cosmos arranged upon circular rings, with small spheres representing celestial bodies. The sun was described as a small golden sphere, equipped with a ray and a pointer. Even more striking was the repeated appearance of the ancient Greek term styrigmos stigmos. It referred to the apparent stationary point of a planet the moment when it seems to stop against the background stars before reversing direction in the sky. That meant the inscriptions were describing something very specific. The mechanism was designed to reproduce planetary retrograde motion, one of the most complicated apparent movements visible in observational astronomy. To understand why this matters, consider what was actually engraved onto the machine. The inscriptions were written in Koine Greek, the common language of the Eastern Mediterranean, during the Hellenistic period. They did not simply list the names of planets. They recorded specific astronomical relationships in numerical form, describing how many revolutions occurred across particular numbers of years. Some of these numerical relationships closely matched astronomical parameters known from Babylonian records preserved on cuneiform tablets dating back to the 4th century BC. This suggests that the Antikythera mechanism did more than embody Greek astronomical knowledge. It incorporated astronomical observations developed in Babylon and translated centuries of recorded celestial cycles into the movements of bronze gears. The inscriptions made increasingly clear what the machine was supposed to do. But the mechanical system that actually performed those functions, the entire gear network behind the front planetary display, had almost completely disappeared. Of the 82 fragments recovered from the seafloor, most of the surviving physical evidence belongs to the rear section of the mechanism. The front where the planetary display had once been mounted survived only as scattered gear teeth, broken shafts, and faint traces of circular tracks preserved in the bronze. Altogether, only about 1/3 of the original machine remains. Everything else was consumed by seawater, crushed beneath sediment, or perhaps still lies somewhere near the wreck site, waiting to be found. Reconstructing the missing section was not simply a matter of fitting fragments together like pieces of a puzzle. To display the apparent movements of the 5 planets across the sky, including retrograde motion, when a planet appears to slow stop, move backward, and then resume its normal direction, the machine required an unusually sophisticated mechanical solution. One possibility involved epicyclic gearing. In such a system, one gear is carried by another rotating component, allowing gears to move around one another while also turning on their own axes. This makes it possible to generate complex variations in speed and direction from relatively compact arrangements. Similar mechanical principles would later become important in European clockmaking centuries after the Antikythera mechanism disappeared from history. Yet the ancient builders had to compress these movements into a mechanism only a few centimeters thick. Many individual gears were smaller than a modern coin and carried anywhere from roughly 15 to 80 precisely cut teeth. Michael Wright, a former curator of mechanical engineering at the Science Museum in London, spent years attempting to reconstruct the front of the mechanism by hand. He built physical models and tested gear arrangements one combination at a time. Wright demonstrated that a planetary system using epicyclic gearing was mechanically possible, but his reconstruction did not perfectly match all the surviving physical evidence, nor could it satisfy every inscription revealed by the CT scans. Some configurations worked mechanically but could not fit within the available space. Others fit the physical dimensions but failed to reproduce the required astronomical ratios. Other research teams faced the same problem. There were simply too many possible combinations. Hundreds of different gear arrangements could produce ratios that came close to the astronomical values described in the inscriptions. But the physical constraints were unforgiving. Shaft positions, gear diameters, circular tracks, and the spacing between mechanical layers visible in the CT scans all had to agree at the same time. There were too few surviving fragments to point directly toward a single obvious solution. Yet there were too many constraints to accept a solution that was merely close. For years, the problem remained trapped at this point. Then a team at University College London decided to reverse the entire process. Instead of beginning with the gears and asking what they might produce, they began with the astronomical numbers the mechanism was required to produce and worked backward from there. In March 21, a research team, led by Professor Tony Freeth at University College London, published a paper in Scientific Reports, part of the Nature portfolio. The team brought together specialists in mechanical engineering, civil engineering, geospatial science, and archaeological science. Their approach began with a simple but powerful idea. If the correct gear arrangement could not be discovered by testing one configuration after another, then start with the outputs. The machine was required to produce and work backward to determine which mechanical arrangement could generate them. The inscriptions on the mechanism recorded astronomical cycles for each planet. These were specific numerical relationships between the synodic period, the interval between two occasions, when a planet returns to the same apparent position relative to the Sun and the solar year. Some corresponded closely to known Babylonian astronomical parameters preserved on clay tablets dating back to the 4th century BC. Others reflected Greek geometrical models based on systems of nested circles, developed within the intellectual tradition that extended back to Plato. The UCL team used these astronomical numbers as their starting point. With mathematical models and computational algorithms, they worked backward to ask a mechanical question. What combination of gears using tooth counts that ancient craftsmen could realistically have produced generally between 15 and 80 teeth, with a module of roughly 0.55 and triangular tooth profiles, could generate exactly the required astronomical ratios? Every possible arrangement was then tested against 3 strict sets of constraints. The first came from the physical evidence preserved in the CT scans, including the dimensions of surviving shafts, the diameters of circular tracks, visible on the fragments, and the spacing between layers of gears. The second came from the inscriptions themselves, which describe the functions of the mechanism and the arrangement of its displays. The third was the available space. The entire planetary gear system had to fit inside the limited volume of the front section, only a few centimeters thick. Only configurations that satisfied all 3 sets of constraints were allowed to survive. The result was a model Freeth and his colleagues called the Cosmos. It was a complete 3-dimensional reconstruction of the front display of the Antikythera Mechanism. The proposed system used compact trains of epicyclic gears mounted around concentric shafts. Together, they could reproduce the apparent movements of the Sun, the Moon, and all 5 planets known to the ancient Greeks across a series of concentric rings. Freeth described it as the first model capable of matching all the surviving physical evidence while also satisfying the inscriptions engraved on the mechanism itself. No previous reconstruction had managed to do that. Price had produced a model that explained major parts of the rear mechanism, but it lacked a complete planetary system. Wright demonstrated how planetary gearing could work, but parts of his reconstruction did not match every surviving physical dimension. Other proposals worked mechanically, but conflicted with the written evidence. The Cosmos model was the first proposed solution that did not directly contradict any known piece of evidence. No surviving fragment inscription or measured shaft dimension clearly ruled it out. The Scientific Reports paper described the result as a synthesis of Babylonian astronomical cycles, mathematics from the Platonic tradition, and ancient Greek astronomical theory. 3 different streams of knowledge appeared to converge inside a single machine. But making a model work inside a computer was only one part of the mystery. What that model suggested about a machine built more than 2,000 years ago, and about the civilization capable of building it, was something far more difficult to ignore. The Cosmos model suggests that the front of the Antikythera Mechanism was not simply a clock face or a reference chart. It was a moving map of the heavens. It was a mechanical model of the celestial system that ancient Greek observers could see from Earth. Across concentric rings on the front display, small bronze spheres represented 7 celestial bodies. The Sun occupied its own ring, represented by a small golden sphere with a ray. The Moon moved on another ring and was connected to a separate mechanism that reproduced its changing phases throughout the month. The 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, each moved along their own circular path, according to their individual synodic cycles, all against the background of a zodiac ring divided into 12 signs. Everything was driven by a single hand-operated control on the side of the machine. Turning the mechanism advanced the system through time. As the gears moved, the small planetary indicators followed their apparent paths across the sky. Their motion could include retrograde behavior when a planet appears to slow down, stop, move backward against the stars, and then resume its normal direction. There was no electricity, there was no software, there was only geometry, bronze, and carefully calculated ratios. At the same time, the rear of the mechanism calculated the Metonic calendar, showing how lunar months aligned with solar years across a 19-year cycle. It predicted solar and lunar eclipses through the Saros cycle decades in advance, and recorded information about the type and timing of those eclipses. It could even track the cycle of major Greek athletic festivals, including the Olympic Games. All of this was compressed into a device, measuring roughly 33 by 18 by 9 centimeters smaller than many modern laptops. At least 30 gears survive in the fragments. The UCL reconstruction proposes that a complete machine may have contained around 69 gears in total, with many carrying teeth less than 2 millimeters in size. Nothing with a clearly comparable level of mechanical complexity appears again in the surviving global archaeological record for many centuries. Sophisticated astronomical clocks later emerged in the medieval Islamic world, and eventually in Europe. By the 14th century, monumental astronomical clocks in European cities began to display increasingly complex celestial cycles through elaborate gearing, but the Antikythera mechanism had achieved an extraordinary concentration of astronomical calculation in a compact mechanical device more than 1,000 years earlier. That gap is one of the most unsettling aspects of the discovery. Not because it points toward aliens or some vanished technologically advanced civilization. There is no need for those explanations, and there is no evidence supporting them. The problem is much simpler. Our surviving picture of ancient mechanical technology may be severely incomplete. Bronze was valuable in the ancient world. A device that broke or became obsolete could be melted down and transformed into weapons, household objects, tools, or statues. The Antikythera mechanism did not survive because someone deliberately preserved it. It survived because the ship carrying it sank before anyone had the chance to recycle the bronze. Had that vessel reached port safely, the mechanism might eventually have been melted into a statue, a vessel, or some other object. If that had happened, the history of technology might never have known that such a machine had existed at all. And ancient literature suggests that Antikythera may not have been unique. Cicero described at least 2 devices with similar purposes. One was associated with Archimedes of Syracuse. Another was connected with the philosopher Posidonius on the island of Rhodes. Cicero wrote that the device attributed to Archimedes could reproduce the movements of the sun, the moon, and the 5 stars called wanderers, meaning the 5 planets visible to the naked eye. According to his description, the machine reproduced celestial movements in a way that reflected what occurred in the real sky. Rhodes, where Posidonius worked, was also an important center of astronomy and mechanical craftsmanship in the Greek world. Hipparchus, one of antiquity's greatest astronomers, had also worked on Rhodes during the 2nd century BC, and several astronomical features associated with the Antikythera mechanism have been compared with theories connected to his work. This raises an important possibility. The Antikythera mechanism may not have been a solitary invention. It may instead be one surviving example of a broader tradition of precision mechanical construction that has almost completely disappeared from the historical record. Not because the technology was forbidden, not because someone deliberately erased it, but because the material from which these machines were built was simply too valuable to leave intact once the devices stopped working. And this is where the central question begins to find its answer. The Antikythera mechanism is physical evidence, not legend, and not speculation, that ancient Greek craftsmen were capable of building an extraordinarily sophisticated mechanical astronomical computer. It could represent celestial cycles, predict eclipses, coordinate calendars, and, according to the UCL reconstruction, reproduce the apparent movements of the planets through a dense network of precisely arranged gears. The Cosmos model did not create that complexity. Its purpose was to test whether the surviving fragments' measurements, astronomical ratios, and inscriptions could belong to a single coherent mechanical system. The answer proposed by the UCL team was yes. The front display could have existed, it could have functioned, and it could have shown the celestial movements described in the inscriptions engraved onto the machine itself. The ancient Greeks did not simply observe the sky. They found a way to reproduce it in bronze using gears, geometry, and mathematics inside a device small enough to hold in human hands. The Antikythera mechanism does not necessarily rewrite history. It reveals how incomplete history can be. For more than a century since its recovery, the machine has repeatedly exceeded the expectations of each generation that studied it. Price identified an astronomical calendar computer. Later imaging revealed an eclipse prediction system and a dial connected with major Greek games. The inscriptions exposed evidence for a planetary display. The Cosmos model then proposed a way for those surviving clues to operate together as one complete mechanical system. Every layer of corrosion removed by modern technology, every newly recovered inscription, every gear and every astronomical ratio hidden for more than 2 millennia has pushed the boundary of ancient technological possibility further into the past. And the investigation is not finished. The UCL team has also pursued the challenge of building a physical version of the reconstructed mechanism and testing whether the mathematical design can operate as an actual machine. If such a reconstruction can be made to function successfully, it would bring us closer than ever to seeing the Antikythera mechanism move again after more than 2,000 years.